You hear that? Okay, so let's go ahead and pick back up with conformational isomers. Okay, where we started digging into that a little bit. And again, we'll go ahead and look at ethane. So remember that ethane, we drew the three-dimensional structure last time, but what we're going to do here is redraw ethane like this here. Okay. Where these symbols represent something. See the big fat circle? That represents a carbon. Okay. And then see where these three lines join in the middle here? That represents a carbon. Okay. So what we're doing is basically we had a eyeball here. We're looking down this carbon-carbon bond. Okay? And so you have a front carbon and you have a back carbon. Okay? So the front carbon is that one there where the lines are, and the back carbon is always where the fat circle is. Okay? What do you think we're going to put on these lines coming off the carbons? The hydrogens. Very good. Pretty simple. Okay? So let's go ahead and do that. So there are our 6 hydrogens. Okay. Let me go ahead and erase these arrows here to get it clear. Okay. And so this projection is what we call a Newman projection. Okay. And as you can see, the purpose of it is that it allows us to see all the bonds to hydrogens. I don't really care about the bond between the 2 carbons. Okay. Or another way that you're looking at that molecule, if you look at this three-dimensional molecule, okay, this is what you're doing. Here's the front carbon, here's the back carbon. You're looking down that bond axis. And all you're cared about are the bonds to the hydrogens. What we're going to do, remember we said that the carbon-carbon bond can twist, it can rotate. And that's what we're going to do. We're going to rotate the bond. And the Newman projection allows us to see those hydrogens where they are per each rotation. Okay? So let's go ahead and do that. So let's rotate this 60 degrees. Okay? Just to let you know, a 60-degree rotation is this angle here. Okay? Between those hydrogens. So when I rotate 60 degrees, okay, let me give you a way to follow this so you can do it on your own. Okay? When I rotate 60 degrees, what I'm going to do, you can write down your notes, I'm going to keep the back carbon the same. Okay? So all those bonds to hydrogen do not move. Okay? So keep the back the same. That's your reference point. Okay? But the front hydrogens I am going to rotate 60. And when I do that, they're going to overlap with the back hydrogens. Okay? So all the bonds overlap. Okay? If you try to draw them right on top of each other, it'd look real messy, but you get the idea, it's close enough. Okay? Then if I took this thing and rotated it another 60 degrees, what would you get there? You'd get back to here, wouldn't you? Okay? That's what we do in Newman projections. We're going to rotate 60 degrees, one at a time. 160 here to get the overlap, and then another 60 to get back to that. Okay? We call these different Newman projections some different names. Okay? Here, where they're all staggered out, that's called a staggered conformation. And here, like when the moon eclipses the sun, this is called eclipse. Okay? So when we do Newman projections, we're always going between what? Staggered and eclipsed. Staggered and eclipsed. Because that's what you get for every 60 degrees. Okay? So any questions on that? I think that's pretty straightforward there. Okay? Now, there turns out to be an energy difference between the two. Okay? Which do you think will have a higher energy associated with it? Which looks like it's maybe more strained? Okay, the eclipse. Okay? So here, what happens is the electrons in the bonds, when they overlap, okay, they're getting pretty close to each other here, okay? And what happens when electrons get close to each other? They repel. They repel. Okay? Okay. So you get the repelling of electrons. And that creates a strain in the molecule that we call torsional strain. Okay, so torsional strain is when you have an eclipsed conformation and those bonding electrons are repelling each other. Okay? And so, as a result, that's going to be higher energy than the staggered conformation. Okay? So, what we want to do is make a graph of that. Let's do that over here. So let's make a plot of energy as a function of bond rotation, or the angle. Okay. So let's say at 0 degrees, we had a staggered. We'll put it down there because that's going to be lower energy, isn't it? And then when we go 60 degrees, our energy will be up there somewhere. be higher. What happens when we go another 60 degrees?
Goes back to 0.
Comes back down here to a stagger. Okay, so that'd be 120, and so on. So we get this kind of plot when we do the bond rotations using the Newman projections, okay? And this is what's called conformational analysis. Okay, 10 minutes late here. See in the way?
Let's do it all the way.
Yes, good one. I'll double. Okay, so that's for the simple molecule ethane, okay? When we're simply rotating this bond every 60 degrees, it costs us energy, okay? And that's why this is one conformational isomer, and this is another. They're both called ethane. What's the difference? The difference is the rotation of the bond. And when I rotate, it gives me a different energy content with it, okay? So that's ethane, okay? Let's go to a little bit more complicated molecule. Okay, let's go to this one here, butane. Okay, butane. If you look at butane, how many carbon-carbon bonds are in there? How many carbon-carbon bonds are there?
3.
3. Okay. So I need to choose a particular bond for my Newman projection. Okay, let's go ahead and choose that carbon-carbon bond. Okay. So if I choose that carbon-carbon bond, I can maybe make this carbon here the front, and that one there the back carbon. So let's make my Newman projection. Showing my front and back carbons. What does my front carbon have on it? It has what? 2 hydrogens, and what else? The CH3. See that? So let's put those on the front carbon here. I have 2 hydrogens and a CH3. Okay. You could have put them on anywhere you wanted to. I just chose that one. What does the back carbon have on it? 2 hydrogens and the CH3. I'll choose to put them on here. Like that. Okay. So notice I'm starting with a staggered conformation once again. Now what do you think we're going to do now? Rotate every 60 degrees and look for what? Energy differences. That's all we're doing. Okay? So now, since we have 2 groups that are different there, now I'm going to have differences between my staggereds and my eclipses, so I'm gonna have a lot of different ones going on. Okay? I'm gonna draw it a little smaller, because we're gonna have a lot. Okay, so remember, you keep the back carbon the same. Okay, you always have to have a reference point. Okay? If I move the back carbon, then it wouldn't make sense. But I do move the front carbon, those bonds. So I get my eclipsed like that. Okay? Just like in this world, if there was no standard of what is good, then what? There'd be nothing good. Okay? You'd have a reference point. Okay? So there's my eclipse there. Now let's rotate another 60 degrees. So again, the reference doesn't change, but the front does. So now those two CH3s are kind of close to each other. So let's continue to rotate 60 degrees. So again, the back carbon doesn't change. And now, making these things eclipsed, it's a little messy here, but we will do our best to get something like that. Okay, so now those two CH3s are right on top of each other. So now let's rotate again. That will bring the CH3 over on the other side. Give us another staggered. And lastly, let's get one more eclipse. Okay. There's our last eclipse. And then if you rotate one more 60, we get back to our original staggered conformation. Okay, so here we've done a full 360 degrees. That CH3 went all the way around the clock. Okay? And we did that because now you can see each one of these are a little bit different. Okay? Any questions on those? Okay, gotta make sure you can label those. Okay, so staggered eclipse, staggered eclipse. Okay. This one down here where in the staggered, where the two CH3s are kind of close to each other, sometimes you'll see that called the gauche conformation. Okay, not a big deal, just sometimes you'll see that in your book there. What's the last thing we want to do with all these? We want to look at what the graph or the energy difference between these, okay? So before we graph those, which of all those do you think looks like it's the lowest energy one? Why is that?
They ain't close together, I
Okay, yeah, so here you're starting to note something good, that a hydrogen atom is very tiny. Okay, so size-wise, if you ever see a hydrogen, it's like a dot, very tiny. But as soon as you have any other atom, carbon or CH3 or chlorine, bromine, so on, those things look gigantic compared to it. Okay, so size-wise, this is what we get. So if you look here, you have the two big CH3s opposite each other, okay? One word for opposite is what's called anti. So this thing here is sometimes called the anti-conformation. If you compared the anti-conformation to the gauche, you would expect which to have lower energy? The anti, because here they're closer. Okay? So here they're starting to get closer, they can start to almost bump into each other. So the gauche conformation has some strain to it that we're going to call steric strain. Okay? So what is the definition of steric strain? Write it down. When you have two non-hydrogen groups getting close to each other. Two non-hydrogen groups getting close to each other. Okay? You can almost call it like bumper cars, bumping strain. Anybody like riding bumper cars? Okay? No? Try it sometime. Have some fun. What other conformation has steric strain? See any others that have steric strain?
The edge in between the two gauges.
This one here. This has what? Even more steric strain. Okay? Because now they're right on top of each other. So this thing will explode in energy here, very high energy. And then this gauche would have the same energy as this one. Okay? So you make sure you're familiar with these two types of strain, because we're going to be using them all the way through 242. Know what torsional strain is, sometimes called eclipsing strain, and know what steric strain is, or bumping strain. Okay? Don't forget those two, very important. So now, let's go to the last step and graph these things. This time our graph is going to look different than ethane, isn't it? Okay. So originally at 0, we had this staggered, which was what? Anti-staggered. So that will be our lowest energy. And then we went to an eclipsed. Okay. Which higher energy. Why is that higher energy? Because it has torsional strain. Torsional strain. And then when we went to the other staggered, remember, it's not as stable as the original because of what? Steric strain. Okay? So the steric strain in this one is keeping it higher energy than that one. Okay? Then after this staggered, we went back up. Why are we going all the way up there? Because that thing's exploding with both what? Torsional strain and steric strain. Those two CH3s are right on top of each other. So that will be our highest energy point. And then we come back to the same staggered on this side. Then the eclipsed, and then the original staggered there. Okay? So make sure you can match each of these points with those Newman projections that we just looked at. Okay? And now all we do is connect the dots. And we get something like that. Okay? So here's a graph displaying the energy differences between each of those conformational isomers. Okay? So what do you want to take away from this? Okay? Well, here are the kind of questions you can expect to see. Okay? One kind of question is, I could draw a graph like this and point to a particular spot and ask you to draw the Newman projection at that spot. Okay? So you have to work backwards. Or another kind of question is, I could say, draw the most stable staggered conformation for the molecule. And so you would draw the Newman projection at that point. Or I could say, draw the most unstable eclipse conformation. Then you would draw it for that, and so on. Okay? Any questions on Newman projections and how to use them? Okay? Very important topic. In your lab next week, you'll be doing a lab on some Newman projections to get some more practice there. Okay? All right, and your homework gives you additional molecules besides ethane and butane to do, okay? So make sure you do those homework problems in the chapter, okay? They'll give you additional ones besides the ones we just did here. Okay. Okay. For example, you should be able to do a molecule like this here. Just taking one off the top of my head. You should be able to take that and make Newman projections every 60 degrees and plot the energy differences, okay? So you can see there I have a couple extra groups on there, okay? So on your own time, make sure you can go back and do things like that. Okay, let's move on here. One topic that, kind of going backwards here, going back to our naming. Let's look at this topic, something called branches. Okay, so what in the world are you looking at there? Okay. Well, let's suppose we had a molecule we wanted to name. Okay, or we had something like that. Okay, suppose I gave you that on the exam and asked you to name it. Okay? What's the first thing you would do? Find the parent chain. Where's the parent chain? Okay, count across. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? If I try to include this, 1, 2, 3, 4, 5, 6, 7, 8. Then I get 8 on that side. So 9 will be the winner, isn't it? So let's go ahead and number the parent chain. Okay. So we have a nonane and we have a branch on the 5th carbon of it. But if you look at that branch, how in the world do we name that? Okay? That's not one of our isomeric ones we memorized, isn't it? It's not an isobutyl or a secbutyl or isopropyl. Okay? This is what's called a branched branch. Okay? What do you mean by that? Okay? So if you look, the longest part of this branch from this connection point, let's put some numbers here, 1, 2, and 3. Okay? So the root part of this branch is 3 carbons long. And what's a 3-carbon branch called? Propyl. Propyl. Okay? So this thing here is a propyl group. But we have some branches on the propyl group. What are the branches? A methyl and a methyl. Where are those on that branch? On the 1 and 2 carbons. So we'll have a 1, 2 dimethyl, a 1, 2 dimethyl propyl. Okay? So that's how we'll name that branch. Since it's a branched branch, the way we let the reader know that is we put that in parentheses. Okay? And that whole thing is on what? The 5 carbon of the parent chain. So we'll put the 5 in front. And then to finish the name, we'll do what? Write nonane. Okay? So this is how we deal with these branches, or sometimes they're called complex substituents. Okay? So I name the branches on the branch, put it in parentheses, then put the number where that whole thing is attached on the parent chain. Okay? Those things are a little tricky. Any questions on how we did that? Okay? Your homework, maybe you've seen, deals with some of those. Okay? So maybe you said, boy, I looked at that homework, I didn't know how to do it. Okay, now you do. Okay? So these are branched branches. Okay? Any questions on this? Okay. Well, let's get into the last part of this chapter. The last part of this chapter deals with cyclic molecules or rings. Okay? So the most simplest ring, remember, to make a ring you need at least 3 points. So the simplest ring would be a 3-membered ring. Then 4, 5, 6, and so on. So we want to first of all look at how do we name these rings. These are very easy to name. Okay, maybe you already know. How many carbons are in this ring? 3. 3 stands for propane. And what you do is put cyclo in front. So we would have cyclopropane. Okay? And I'm willing to bet that you can name the other 3. What's the next one? Cyclobutane. What's the next one? Cyclopentane. And what's the next one? Cyclohexane. And you can keep going. Okay, so I'll let you fill in the other 2. Okay. Cyclohexane is the most popular one. We'll see why as we get into studying it. Okay. Well, sometimes on these rings, we have branches or groups on them. So let's see how to handle those. Okay. Here we have what kind of branch? Methyl branch. So we simply put the branch in front of the ring. So we have methyl cyclobutane. Do I need a number with that branch? Why not? Because any one of these carbons, there's no beginning, there's no end, is there? So when I have one branch, any of the points are the same. So I don't need to use a number. Okay? I do need to use a number if I have more than one branch. Okay? So make a note of that. So if I have more than one branch, have something like that. Something like that. Okay, these two are what? Isomers of each other, aren't they? I just have different positions where the CH3s are. And how do I know they'll be isomers? Because they'll have different what? Names, different names. Okay? What will be the name of this one? Okay. Now, I have to tell you they're on the same carbon, so it'd be 1,1-dimethyl. Cyclobutane. Okay? That's the only way I can tell you that they're on the same carbon. If I just put dimethyl cyclobutane, well, you don't know where they are. Okay? So now numbers always give you a reference point. What will be the name of this one? 1,2-dimethyl. Okay, so these two are isomers. What kind of isomers are they? Are they conformational isomers? What kind of isomers are they? Structural isomers. Those are structural isomers. Why? Because they have different structures. And structures, different structures will have different names. Just like you could have a structure for a parking garage, would have a different name than this building, which is what a classroom building. Question?
Is it always that in the upper right corner, is it always the number one carbon?
No. You could have made either of these one. Doesn't matter.
How do you know which one?
Doesn't matter. Your choice. Your choice. You like that? Let's come back to this one here. When you have two groups on different carbons, you can end up getting two more additional isomers.